Dear conference participants, this report is dedicated to describe how it's possible to organize education process for technical engineering students, so these students can proceed fully functional remote laboratory work using only real laboratory equipment and without using any virtual emulators. Really, the traditional educational system assumes that a lot of people must meet together in one room, but unfortunately, there are reasons specified here that does not allow to proceed a traditional education process. As a result, educational institutions are forced to implement various electronic educational mechanisms. A new and original approach to controlling an arbitrary laboratory device is presented. Such device can include a limited number of buttons for manual information input and an indicator for visual output the information. The main goal of this work is ensure effective operational interaction between teacher and remotely connected students. The learning management system can be easily replicated because it consists only popular and globally used components. Particularly, 7 copies of such learning management system has been already created. The system has been successfully operated in our university for 2 years. As an example presented in the article, the object of student research is the programming of ATmega 8 microcontrollers using a development board with these controllers. The development board contains a matrix with ATmega 8 controller, digital screen with 7 segment indicators, and 4 buttons that can be pressed simultaneously or in any sequences. The board is connected to a 10-pin cable to a USB ISP programmer. And this programmer is connected to the USB port of any workstation or laptops. Previously, students worked with such development board directly, but now, unfortunately, students cannot connect development board to their laptops directly and work directly with it. Therefore, to fully replace such traditional work with development board, a laboratory learning management system was created consisting of the following hardware components: a development board with an ATmega 8 microcontroller, USB ISP programmer, microcontroller chipkit UNO32, to which a 4-pole relay is connected. Microcontroller plays the role of student's remote hand. Students can independently press the buttons of the development board in any combination and in any sequence. A web camera that directed to a board allows students to observe its current state in real time. Any workstation or laptop with the operating system Microsoft Windows that can be accessed remotely using remote desktop protocol. All of show components make up one instance of a learning management system. Workstations or laptop must have 3 USB ports. The first port used for the USB ISP programmer. The second port is used for chipkit microcontroller, remote hand of student, and third port is used for a web camera. As a result, any authorized student located in any country in the world can connect to this workstation remotely, develop, debug, and burn a compiled C program for the ATmega 8 microcontroller to the development board, run it for execution, press the buttons using chipkit microcontroller, and look through the camera to the 7-segment indicator. To start lab work, any student receive IP address, TCP port, and network credentials. For example, student 1, and open remote RDP session from this home computer to internal education computer. One more student also can log on to the same computer, but with a different login student 2, and one more student with login student 3, and so on. Sure, students need to understand that some operations they can do simultaneously, independently, and on the contrary, other operations they can do strictly sequentially, only one after the other. Usually, the average student writes a C program using the integrated development environment IVR Studio in about up to 1 hour, 60 minutes. When then a user must check the program operations. So he spends approximately 5 minutes on burning compiled C program to the Atmega 8 microcontroller and checking the program operations. You can see that most of time students spend for developing the C program without using devices connected to the computer's USB bus. Obviously, many students can do this part of the work on one computer at the same time. In order to press the buttons on the development board, students must use a PATI program that interacts with microcontroller chipkit UNO32 via a serial interface. When the user successfully establishes a connection to controller chipkit, a short instruction on the screen appears. Enter 4 digits. 1. Button not pressed. In other words, permanently release it. 2. Button is pressed, but after 1/2 of second, release it. And 3. Button is pressed permanently. So, student must enter a command. It consists of 4 digits from 1 to 3. For example, 3 1 2 1 1 2 1 1 2 1 1 3. Buttons are numbered from left to right. 1 button, 2 button, 3, and 4. Therefore, in order to press and release button number 1 and not to press other buttons, user need to execute the command 2 1 1 1 in order to press only button 1. Similarly, in order to press and release the button number 4, user needs to execute the command 1 1 1 2. Number 2 must be just in the position 1 on the first command and on the position 4 on the second command. Finally, command 2 2 2 2 presses and releases all 4 buttons 1 2 3 4 sequentially. Instead, to control a program running on Atmega 8 microcontroller, it may be necessary for different buttons to be pressed exactly at the same time. It's easy to do, but user need to execute not one, but already 2 commands in sequence. Example 1. In order to simultaneously press button 1 and 4, 2 commands must be executed. First command 3 1 1 2 and second command 1 1 1 1. Digit 3 on position 1 presses and holds the button 1, while button 4 is also pressed. Command 1 1 1 1 is required to release all buttons after button presses at the same time. Example 2. In order to press all buttons 1, 2, 3, 4 simultaneously, 2 commands must be entered 3 3 3 2 and 1 1 1 1. As a result, the students can operate with real laboratory equipment, develop a C program, compile and run it on Atmel microcontroller, press the buttons remotely, and see indicator user a web camera. In combination with network platforms for collective interactions, the students will also be able to consult with teachers and other students, demonstrate his screen, and report on the completed laboratory work. Online platforms for collective interaction only allow the lecturer to demonstrate the correct performance of laboratory work. However, it's possible to build a specialized network channel, which allows authorized users to provide reliable access to the computer in the internal private network of the educational institutions and to all programs running on these computers. An almost unlimited number of students can work remotely on the same computer. Sure, different students must use different own logins. If one copy of a specified program, specific program is installed on one computer, several students can remotely log in to this one computer and run these programs successfully. For example, integrated development environment AVR Studio at the same time. Laboratory computer on which students work remotely can have an additional microcontroller to which an executive device is connected, for example, a multi-pole contactor. Such device can help the students remotely press button and change the position of the switches of the laboratory equipment. Students can observe the laboratory equipment, laboratory hardware using a web camera. Thank you for your attention.